Thank you very much. So, yes, I'm Noam. I'm going to give the talk, but most of the credit of this work should go to the student who couldn't be here, but she did most of the work, so Shelly Grossman. And this talk is going to be about online detection of effectively callback-free objects with application to smart contracts, as I just said, and this title is long enough to almost be entitled to be an abstract. But the motivation for this work is actually can be summarized in 2 words: modular reasoning. What we want to do, we want to reason about systems which are comprised of a collection of interacting components, where every component contains its own state and a set of methods, which only it can use the state. Only these methods can use the state, and the components interact by invoking methods of one on each other. So the system is driven by users invoking methods from the outside world. So once a user invokes a method, the method is run until completion, and then another method can run, etc. And the systems can evolve by having new components put into the system, and even existing components can be modified to behave differently. So this is the system that we are interested in, and you might wonder why we care about these systems. Well, this is a pretty accurate description of the kind of systems which are used to execute smart contracts, like Ethereum. This is kind of model of the operations. So we want to reason about them, but before we want to reason, what kind of reasoning do we want? So these systems are very dynamic. Multiple vendors can create different components. So I cannot even trust that when I invoke a method on a different component, it will be the same component that I invoked the last time. So in a sense, the only sensible thing to have is a sort of a modular corrective conditions, where I verify the correctness of my component in any possible context, in any possible environment in which it can be executed. And if this is the kind of environment that the corrective conditions they care about, then I might as well go to modular reasoning, because I do not know what is the other code. So I want to reason about the code of the component only by its own, looking at itself. So what is the challenge here? Well, we have a very strong notion of encapsulation. Every component has its own state, and only the method of the states can manipulate this state. So are we done? Is it enough to basically do modular reasoning based on these premises? Because let's see this simple example where we have a blue module which has a single variable initialized to 100, and it has a method called decrement, which gets a value A, and it checks if the value is smaller or equal to X, then it logs the fact that it's going to decrement A and does the decrementation. So we might think that this is a very simple module, and we want to reason about it. The problem is that we don't know what is the code of log. However, in our setting, log doesn't have any effect essentially on the blue module, because we can only interact using invoking method calls, and the only possible effect that the red module can have on the blue module is the return value, and here we don't even look at it. So we optimistically just say, well, let's just ignore the call to log and do the reasoning. So let's see. Once the module initialized, x is greater than 0, and if we assume that x is greater than 0 and decrement is invoked, then before you do decrementation, we actually check that x is bigger than a. So we hope to conclude that indeed this invariant holds. Unfortunately, this is not true. And let me show you an example of an environment in which this kind of modular reasoning breaks. So let's look at the blue module that we saw before. And it's run in a context where the red module, the only thing that it does is non-deterministically decides to call back into the blue module and invoke the decrement argument, the same argument that was passed to it. So let's run through an execution of this module. We start with the state where x is equal to 100. And then the user invokes the decrement method from the outside world. The blue module starts executing with the decrement 100. And it checks that the condition is okay because A is equal to X, and it invokes the red module with the log. What the log does, it decides to call back into the module to the blue module with the value 100. Here, again, we check the condition holds, so we call log again. We go to the condition, we call log again. This time, log does nothing. Now, the stack starts to unwind. We go back to the blue method, and we set x to 0, because we do x equal x minus a. And then we return to our call, to the red color, and again, go back, unwind the stack, go back into the case where we just, after the first call to log. Here, we do the decrementation again, and we get into x equals minus 100. So we broke the invariant. So why did it happen? Right, well, because it was not an invariant. We assumed that, or that doesn't hold, but why did that didn't hold? It didn't hold because our assumption that when we invoke a log, that x is equal or greater to a, when before the invocation will carry out after the invocation, is not true. And this was the problem that basically broke our reasoning. So actually, this is not a new problem. We've seen this before in other names like reentrancy, where basically the idea is that if we have, for example, some invocation of the blue method on this call stack, we call the red module, and the red module calls back into the blue module, then either the second invocation, you can see changes to the state of the object that happened before in the first call, or it can make changes that might invalidate our reasoning about the fact that the state of the object doesn't change by calls to the outside world. And this is kind of been known to be like a can of worms all the time. So so this is the problem that we're trying to solve. How can we do modular reasoning in the presence of callbacks? So one simple answer to it is just let's forbid callbacks. If there are no callbacks, there are no problems. Well, the answer is the short answer for why we don't do it is that we actually need it. And the longer answer is that in this kind of system that I just showed you about, where the encapsulation is so strong, the only way of communicating between the different modules is the use of the calls and returns. So callbacks are essential to facilitate communication between the components. And in fact, if we looked at the entire execution of the Ethereum blockchain, and we see that callbacks are being used more and more as the blockchain evolves and progresses, and people write more and more sophisticated code. So we need callbacks. So what do we do? So what we do in this paper is that we give two correctness conditions, which if your execution satisfies them, or your object satisfies these executions, and actually they are the same AD, but two flavors of it, then basically it allows you to tame the callbacks. You can use callbacks, but the callbacks cannot do nasty things, and thus it enables modular reasoning of the kind that we've just seen. So let's go for the first one. First one is called final state effective callback freedom. And I need one definition before I go into the details. I'm saying that an execution is complete if it starts with an user invoking a method from the outside world, and it executes until it returns to that user. So you don't return in the middle. And I'm going to say that an execution pi is a final state ECF. And I'll walk you through the definition. If, let's say that this is the execution, and it starts when the user invokes it, or invokes the method on state S0 and ends at state Sn, then for this execution to be effectively callback free, final state effectively callback free, and note that this execution actually has a callback because we have here the blue method at the bottom, there must be a sequence of complete executions, execution comprised of a sequence of user invocations, which doesn't contain a callback, where in the first state of the original execution and in the new execution, the state of the object O is the same, and at the end, it also O is the same. So from this point of view, we produce the same state of O using the new execution pi prime. Now, I want you to notice that I didn't require it to be from the same system. So pi can be produced in one environment and pi prime in a different environment. I don't care. All I care about is that there is an environment which allows you to produce pi prime, in which pi prime can be executed. So if we look at our problematic execution from before, then you can see that this is actually, execution is actually non-ECF. It's not possible to start an execution without callbacks in a state where the x is equal to 100 and end in x equal minus 100. However, if we do a simple fix and basically turn the call to log into a tail recursion, then we get a new module where in which it is okay to execute callbacks, but we never get into the problem because in a way, before we do our change before we call the recursive method, and thus we don't go into a second call to log. We don't go into this again. And although we have a callback here, this execution produces a state which can also be produced as if log didn't call back to the module. So if you think that this is a stupid bug, then I just want to, well, it is a stupid bug, but it's real in the sense that if you look at what happened 1 year ago, there was a bug in DAO, which is a very big contract that was executing on the Ethereum blockchain, which was basically used to pull together money of multiple people and use it to invest based on some voting system between the people who participated in the DAO. And someone basically used a loophole, which was made possible because of non-ECF behavior of the method of the DAO, to steal temporarily 3.5 million Ethers. I'm not going to tell you how much it was now, but what happened essentially was that the same mistake that we had before. What the DAO had, it had some sort of, it pulled all the money together, and it maintained a table of how much every person put. So when someone wanted to withdraw the money, it checked the table, see that this person has indeed money in the account, sent the money to the person, and you send the money in Ethereum by invoking a method on the contract representing the other person, and you can see it here by invoking the send on the person who asked for the money. And after the call returned, I set its balance to 0. However, the person who attacked the contract, when I called it, it called me again using a callback and basically pumped out money out of the DAO, although he was not allowed to do it. So this is what happened in the DAO, and in order to fix it, they basically had to break the promises of the system that you don't rewrite history and then to roll back the blockchain, and this called a lot of controversy. So let's go back to science. And we had the notion of ECF, which was in dynamic because it talks about particular executions. And essentially what it said is that the state produced by execution with callbacks can also be produced by an execution without callbacks. So we don't get any surprising states even if we have callbacks in the system. So it's very natural to lift it to all possible executions. So we say that an object is a static ECF, final state, if every of its complete execution is final state ECF for that object. And if we know that indeed the object is final state ECF, then we can use the kind of modular reasoning we've seen before, and it is indeed modular. And it is modular reasoning, it is sound, because we know that callbacks cannot affect our reasoning. Actually, if we enforce the ECF property by changing the semantics to be a stronger semantics, then the kind of problems that we've seen before are removed by construction, and actually this module that had the problem without the call recursion, that had the problem in the standard semantics, we can also reason about it using this kind of reasoning because the system will enforce the ECF property. So this is all good and well. Unfortunately, if we want to verify that an object is ECF, final state, it's undecidable. It is decidable if it is finite state, but the domain of elements come from finite domain, but in the general case, it's not. And even if I give you a single execution, even an SQ, this execution, final state ECF, is still a problem is undecidable in general. So what do? We go to a stronger notion, which we call conflict effective callback freedom, where essentially if you are familiar with conflict serializability, you will not be very surprised. What we are saying is that an execution pi is conflict effectively callback free if we can look at the execution, and we identify basically the different invocations, and we treat each of them as if it is a transaction. And we can reorder the invocation in such a way that we produce we get an execution. This execution has no callbacks, and it preserves the same order of conflicts as in the original one. So basically what we got here, we got a permutation of the same events occurring. And again, we allow this new execution to be produced by a different environment. So we can lift again the notion of ECF from dynamic to static by saying that an object is conflict ECF if all of its complete execution are. Again, verifying this is undecidable and becomes decidable if the data come from a finite domain. However, in this case, the problem of checking whether a given execution is ECF is decidable, and actually polynomial. So this is exactly what we did. We implemented an algorithm based on standard conflict graph detection, which tracks the reads and writes of operation of every method invocation. And we implemented it inside the Ethereum virtual machine by instrumenting this execution, and used it to basically explore what happened on the blockchain from its inception. And currently our monitor runs in a detect mode, and it just reports violation, but it's very easily to basically use it to block non-ECF execution by basically aborting the execution. So what did we find out? Well, if we look at what happened in the from the inception of the blockchain, of the Ethereum blockchain until the most important date, which is the POPL deadline, we find out there were about 340,000 contracts, 96 million invocation of methods. Out of these invocations, around 1% was callbacks. And out of all of this, only 3,000 and something invocations didn't satisfy our condition. So if we break in and see which invocation did not respect our condition, we see that most of them actually belong to the code that attacked the DAO contract. The rest are basically 10 comes from another contract which has a similar vulnerability as the DAO, and this vulnerability was reported to the authors of that contract before the DAO, but they didn't fix it. Another 3 were used by company as a dummy exercise to train people how not to write contracts. And another one was used as a way to explain to other people in a blog what was the problem with the DAO. So essentially, if we use our monitor, we detect attacks if you're looking for non-ECF executions, and we had 0 false positive ratio, which is very good, I think. And also the performance is pretty good. We had some 3.5% overhead time and 17% overhead with the instrumentation with respect to memory. And we actually expect this overhead to be smaller in real environments because we used a very non-realistic setup where we basically first downloaded all the blockchain into our own computers. So we didn't use any network. And instead of using standard hard drives or SSDs, we used the RAM disk in order to make the execution very fast. So this is not a standard hardware, but so in real world, it's going to be faster. So this is what we did. And to summarize, what we show that is that callbacks are ubiquitous and are pretty important in current systems. We designed 2 kinds of correctness conditions, which allows you to use callbacks, but in a tamed way, and which in particular enable modular reasoning. And we created a monitor which can be used to detect or enforce the notion of conflict ECF. At the higher level, there is now a lot of hype about smart contracts, etc. So there is a hype, but there is also something interesting here, because the way that contracts are being executed is slightly different than the kind of models we are used to. So we have new challenges, new opportunities. So it is interesting, despite the hype, to look into it, and there are some scientific challenges there which are interesting to explore. So this is the end of my talk. And if there is something that I would like you to remember from it, is that we defined the two practice conditions, which allows you to use callbacks in the same way. And if you are interested in finding the code, the TR with the more details, you can find them there. Thank you very much.
We have time for questions.
So when you show the performance figures, can you move back the slides? One more, yeah. Yeah. So yeah, when you say you check out these callbacks and invocations, do you vary the parameters, or when you say there's this many invocations, are they running with the particular inputs?
Oh, maybe I wasn't clear.
Right.
What we did, we took the entire history of the blockchain. There is one history that everybody agrees of what happened. This is the real history.
Okay.
We analyzed it, and this is what happened in real life. This is not a syntax. This is the one execution of importance.
I see. So it does not guarantee that in the future, under some different inputs, you might see some false positive or...
Obviously not. This is just a testing, a monitor. This is you can look at it as anecdotal evidence. We are currently working on trying to do two things. First, to verify it. Okay. And second, we are working on integrating this monitor into the standard EVM. So it will be possible to execute the standard clients or the standard EVM with this check all the time. So we will enforce our property.
I see. So my second question is that you showed this definition of a callback freedom. How that relates to linearizability?
How does this relate to linearizability? Well, I think it's different in the sense that we don't here talk about, it's more like, I would say, serializability than linearizability, in the sense that we have two notions, the final state and the conflict. And what conflict serializability says is that you can permutate the action of the different transactions in such a way that you execute them as is, and you get the same conflicts. And final state basically says that you will be able to get the same final state as if you the one you started with. So this is more like this. Linearizability talks about the abstraction, and we don't talk here about the abstraction, about the specification of the component.
Okay, thank you.
So these callback-based attacks are an example of reentrancy attacks. And I'm wondering, what reentrancy attacks would not be covered by this? Because I was rather surprised by your results, because there are other known possible reentrancy attacks, which I presumed had been exploited, though they were not specifically the DAO. So how does a callback attack, how does the class of callback attacks relate to the class of reentrancy attacks?
Well, let me answer what I understand. And the issue, when I write a contract, let's say that I'm a designer, I reason about it, and I think about it as if when there are no callbacks. I can think about it as if there are no callbacks. Basically, that when I go outside of the method, when I return, it's the same state. So if I verify that my code is correct in this setup, and the system enforces the ECF, then basically my contract will be correct even if there are callbacks. So this is, in that sense, we give protection. If I'm not didn't answer you, I'll be happy to talk offline.
This is a textbook example of the kind of attacks on smart contracts that would come from this community. So have you, until today, could have been a 0-day attack, right? So, but now you published it. Did you actually execute it? In the sense
no, we didn't find the attack. This is not our attack.
I mean, did you analyze the contracts and see if you can extract, money out of Ether out of them?
Well,
analogous to the DAO?
People actually use the attack to take money out of the DAO. I don't understand the question.
Well, I'm asking whether you did it.
No, we didn't do it. No. Right. We actually found some contracts which have similar issues, and we contacted the developers, and it was the ones that were used for the training purposes. We didn't try to steal money out of these contracts.
Steal? I mean, people would say this is part of the contract, right?
Well, there is money and there is POPL, and POPL is more important.
I think it's an interesting funding model for research, so, you know.
Any more questions? So let's thank the speaker again.